Hello, so in this video we're going to look at something called logarithms, so up to now throughout this chapter so far we've looked at exponentials. So these are expressions or functions of the form a to the x, right? So where x is a power, okay, it wasn't x squared or x cubed, right, where x is sort of the main number, it's now the power, okay, that's what we looked at. So for example, we saw 2 to the x and even e to the x, right, this special number e, where the derivative, right, if we differentiate e to the x, we still get e to the x back, okay, we saw that, right? So these are examples of exponentials. So then the a is the base, that's what we called it, and x is my power, okay? And x was my input, right? In the function, I input my power x, and then it gets me the exponential, okay? So if I sort of, if we break it down a tad bit more fundamentally, what we had was we started with a number x, and so what exponentials are doing is effectively we are raising, we're taking an exponential, which means which means that basically we raise something to the power of x, so we get a to the x, right? That's what exponentials are dealing with, right? Where we have an input x, we have a number x, and x is my power. Right, so I'll raise a number to the power of x, okay? That's what an exponential is doing, right? Okay, but what my question is, what if instead we started with this, right? Let's say we started with my exponential, and actually, what if we go in reverse and try to find the missing power x? Right, so for example, if we had let's say 2 to the x is equal to 4, well, clearly you know that 4 is 2 squared, so here x is 2, right? So in cases like this, we can easily go back, we can easily find the power x, right, if we're given the sort of exponential to start off with, right? But in cases such as 2 to the x is say 13.5, it's pretty much impossible to just work out manually, right? But just spotting what the solution would be, it'd be a very nasty number, right? And actually, it turns out that the value of x here, the power of x, is this decimal 3.7548 ... and it keeps going on. You know, you wouldn't be able to spot that obviously just by trying to guess something, right? Compared to here where x is 2, we can see that clearly. We don't clearly know what the power x will be here, okay? So this kind of motivates to try and find a sort of inverse operation, right? Instead of taking an exponent, instead of raising to the power of x, how do we find the power of x, okay? And actually what this is a logarithm, so we could do something in reverse by taking a logarithm, okay? So a logarithm is the inverse of an exponential. So instead of raising a power of x, we're now going to undo that and try and find the power of x that is raised, okay? Like in these two instances here, where we're trying to find the power of x, right? And so what a logarithm is, I guess more explicitly then, it's this, right? Log little a, then big B, okay? And I use brackets here, okay? B. So what this tells me is this is equal to x. Okay, and so what this tells me is essentially this is the same as saying, as we just discussed, right? I use these two arrows, which means it's going to be equivalent to the same as saying the exponential of a to the power of x is equal to b, okay? So what essentially a logarithm here is saying is, this logarithm tells me the power x here, okay? It gives me the power x. So the a here, so the a here is the base, right? That's my base. B is the whole exponential, right? It's what that exponential equals to, right? And so x is my power, okay? So I'm going to write that here, power base, and B, I'll call it the exponential, right? The whole exponential, right? A to the x, right? That which is equal to b. And so actually, what you'd notice is, as well, is what you'd notice is that I use bracket. I'm going to get rid of this here now, just to make it show you clearly. I put brackets around the b here. That is because with a logarithm, the exponential is my input, okay? And it outputs x. So the power or the output it gives me is x, right? Or what it gets me. Compared to an exponential, x is my input, right? Or my power, right? My power, my exponent. A is still the base, and b is, well, the exponential or the output, right? Right, so if I then if I raise my base a to a power of x, that gets me b. That gets me my exponential, right? And and that's my output. However, the roles are flipped. Okay, with a logarithm, my input is now the whole exponential, and then it outputs the power. Okay, so it outputs the original power. Okay, but the bases are the same. Okay, and you'd notice I don't. The input isn't a base. The base is just a number, right? So a base is the same. It's the same in both the logarithm and the exponential. And so what my logarithm is saying, it says what power. I use question mark, right? Gives me a to the base a, right? The base a to the power of question mark equals my number b, right? So if I raise a number a, well, what power is it being raised by to get b? That's what the logarithm tells me, okay? It tells me what power, what question mark, right? What power gives me that expression. Okay, it looks very, very complicated, right? So we're going to look at some examples. Let's have a look at this example here. So if I get rid of some of this now. Okay, let's have a look at this example. So we said that 2 to the x, 2 to some power x is 4. What's the power x, okay? And we saw that x was 2, right? And so as a logarithm then, what we would say is that the log of the base 2, and it's 4, right? That's my exponential 4, it equals 4. If I do log 2 to the 4, that should get me my power of 2, okay? Now, you can access this on the calculator. There's a log function in your calculator somewhere. Trying to find it on my here. So it's underneath. It's above the cos button, the cosine button, right? It says log, and it should be like a square and a rectangle shape. Okay, it's above the cos button on my class whiz, and so what it gets you is log, and then a small box, and then a bigger box in brackets. The small box is a. So in here it's 2, and then you got, in fact I'll do it here. So the calculator will get you log, there's a small box, and then brackets and a big box, okay? So in this example here, it's when we press the log button, we get this on my calculator. The small button is 2, that's my base, right? And then 4 is like my exponent, right? That's my exponential. It's what it's equal to, okay? If I put that in the calculator, I get 2, okay, which is there, and so that gets me my power, okay. So make sure you are very familiar with that on the calculator, that log button above the cos button, okay. We could do the same for this as well, okay. So if we were to write this as a logarithm to get the power x, right, this is how we would get x, right. Obviously, I just told you what x was here, but the calculator would give me that value, which is how I found it out. So we start with this exponential expression, right? 2 to the x is 13.5. That means we do log of my base, which is 2. So always remember again that the base is the number. It's the number being raised to a power, right? So 2 here, and then it's equal to 13.5. If I put that in the calculator, I should indeed get 3.754, and that would be x. That would be the power. Okay. Okay, so that is basically logarithms. I'm gonna do loads of examples now. Making sure you're very familiar with this logarithm notation. But you need to know that exponential, that logarithm. I write it up here. A logarithm is the inverse of exponentials. So at the end of the day, what you need to know of a logarithm is it tells me, it gives me the power x in my exponential, okay? We can go backwards. Instead of raising something to the power of x, a logarithm tells me what the original power of x is, okay? So this diagram might help you there, but yes. So we're going to look at a bunch of examples now, okay? So we firstly need to write each statement as a logarithm. So we have 3 squared is 9, kind of what we just did. So that's an exponential expression. So as a logarithm, that means we're going to have to take log. Our base is 3, but the exponential it equals 9, okay? And so that should equal my power, okay? It gives me my power of 2, okay? Make sure you confirm that in your calculator. If you put in log 3 and 9, you should get 2 out from the calculator, okay? Right, so then part B, we have 2 to the 7 is 128. So as a logarithm, we would say log of my base of 2, and then my input, well, my input is equal to 128, okay? And so that would equal that would give me my power of 7. Right, part C, we have 64 to a half is 8. So then as a logarithm, that would be log, my base is 64, and then it's equal to 8, so I'm going to put 8 in, and that will equal half, okay? Again, check that with your calculator, right? So that is the statement as a logarithm, okay? So it gives me a way, if I'm given an exponential like this, an exponential expression, I can deduce what the power is. So notice all the logs here equal my power. 2, 7, a half. Okay? That is the fundamental idea with a logarithm. It gives me my power. Okay? Okay, example 7, we now need to rewrite each statement using the power. So we need to basically go in reverse. So now we're given the logarithm. So that tells me write it as an expression, as an exponential, right? So again, that's if we go in reverse, our base is 3, and then it gives me my power. Okay, so the power is 4, so the base 3 raised to the power 4 equals 81. And actually, hopefully that does make sense, because 3 to the 4, hopefully you can realise it's 81, right? 3 times 3 times 3 times 3 is 81. So that should make sense. Part B, we have log 2 to an 8th is 3. Minus 3, sorry. And so then, if we convert that as an exponential, well, our base is 2. And then our power, well, it gives me my power of minus 3. And then that has to equal an 8th, okay? Right. Right, okay, and that's the key. Hopefully, you notice the the key idea that the inverses, because with a logarithm, my input of an eighth is now the output of my exponential. Conversely, my output in my logarithm is the input, my input power in the exponential. So the opposites, right? The input of one function is the output of another, and the output of one is the input of another. That is inverse functions, and so yeah. So hopefully it made sense. And again, 2 to the minus 3, we can confirm it to ourselves if we use power laws. That's 2 to the minus 3 is 1 over 2 cubed. Well, 2 cubed is 8, so an eighth. And there we are. Okay, so that makes sense. Okay, then it says, without using the calculator, find the value of the log. Firstly, the log of 3 to the 81. So, as an exponential, well, we want to find out what it's equal to, right? What's the output? Okay, so question mark. But what this is saying is, then our base of 3 is raised to this mystery power, right? And it equals 81. Okay, well then at that point, how can we find this mystery power? Well, actually, I notice 81 is power of 3, right? 81 is 3 to the 4, I believe. Yes. So 3 question mark, 3 to the power of question mark is 3 to the 4. Well, then our question mark is 4, so that means it has to be 4. Okay. There, right? So that is basically what the logarithm is saying, right? As a repeat, it tells me what power it must be in this situation, right? What power is question mark? That's what that's telling me there. Part B, we need to find log 4 of 0.25. Okay, so again, that's saying 4. If I call that x, then right, I don't know what it is, but if I call that x, you can use question mark. That's fine. But if we use 4. So what that's saying is 4, that's my base, to the power of x, right? I don't know what x is. That has to equal 0.25. Well, how can I find x? Well, actually, again, I'm going to need to do the same sort of thing of using power laws to simplify to help me see. Well, 0.25 is a quarter, right? So then it should be a bit more apparent now. I can write that as a power of 4. So 4 to the xn, that's reciprocal, so it's 4 to the minus 1. Therefore, x is minus 1, which means the logarithm gives me minus 1. Cool. Part C, we have log of 0.5 to the 4. Okay. So then, again, that's going to equal x. I don't know what that's going to equal to. But again, that tells me that 0.5, my base, raised to this mystery power, has to get me 4. Okay. So then, well, again, I'm going to need to use power laws. This 0.5 is a decimal as a fraction. That's a half. So a half to the power of x is 4. Right? Well, actually, then this half, I recognise actually both. I can rewrite both half and 4 as powers of 2, because a half is 2 to the minus 1, right? So 2 to the minus 1 lots of x, and then 4 is 2 squared, right? And so actually then at this point, I can use the power law where I've got a bracket multiplied by power. I multiply the powers. So 2 to the minus 1 times x is minus x. And that equals 2 squared. Therefore, we can see that minus x is 2, so x is minus 2. So again, the logarithm then has to equal minus 2. Part D, we have log of base a to the a to the 5. Okay. And so then, what that's saying is, in terms of exponentials, again, that's going to equal some power x. So that's saying a to the power of x, and this power, right, has to equal a to the 5. Well, it's very easy to spot then that x has to be 5. And so that has to equal 5 there. Okay, so hopefully starting to get a bit of a sort of idea now behind logarithms, right? About what it means, about how we use it to find missing powers. Okay. Um, okay, cool. Now example 9. Use your calculator to find the following logarithms to 3 decimal places. Okay, so this is just testing if you can use the calculator. So as I said, it's above the cosine button, the log button. Again, on the calculator, it looks like log with a square that's filled in, at least on my calculator, and then a larger rectangular button. So if you press this button on your calculator, which is above the cosine button, the cos button, if you press that, then it would come up with log, a small button, and then square bracket and the bigger box, right? And again then, so if we use that then for part A, log 3 to the 40, sorry. Well, that means if we press what I just said, press the log button, the small button is your base. So I put 3 in here, and then 40 in the bigger box. If we put that in, you should get 3.358 to 3 decimal places when rounded. Okay. If I do the same for part B, log of e to the 8. So again, e is just a number. E is next to the ons button. It's the same as where you press pi. So pi is in yellow, E is in red, the alpha mode. So E, again, remember, is this number 2.718 ... That's on your calculator. So you're gonna have to press E in the small box here. So if I get rid of the numbers here, E is going to have to be in the lower box, and then 8 in the bigger box. If you do that, you should get 2.079 to 3 decimal places. Okay. Then part C, we have log 10 to 75, and again the 10 is the first box, the little box underneath, and then 75 in the big box. If you do that in your calculator, you should get 1.875 to 3 decimal places, and that's it. Okay, so make sure you're quite quick and quite proficient and bound to work with the calculator with that. Okay, and again, as a reminder, as powers, what this is saying is that the base, for example, part A, the base 3 to the power which we found out of 3.358 equals 40. Okay, and in part B, log e to the 8, well, that's the base e to the power of 2.079 equals 8. And then part C, 10 is my base to the power of 1.875 equals 75. Okay. And so there we are. Okay, so we've got some exercise questions on this. And so a bit more trickier questions. So it says, without using the calculator, justify why the value of log 2 to the 50 is between 5 and 6. Okay. So in other words, we need to show that it's between 5 log 2 to the 50 and 6. Okay. Well, again, what is this log saying? Well, if it's equal to something, right? Equal to x, let's say. Well, again, convert that back into exponential form. That's saying the base 2 to the power of x equals 50. Okay. And so then, if the logarithm here is between 5 and 6, well, what happens if x is 5, and then what happens if it's 6, right? Let's see what happens. So if x is 5, then 2 to the 5 is equal to what? Well, that you just work out, right? 2 to the 5 is 32. That's less than 50, right? But we'll note that. And then if x is 6, then 2 to the 6 is going to be 64. But hang on a minute, between 5 and 6, between the powers 5 and 6, we've gone from 32 to 64. But 50 is in the middle, right? 50 is somewhere in the middle between the two, right? And so there we are. So that's essentially it. Okay. I guess as a written explanation, I note that 2 to the 5 is less than 50. Well, 2 to the 5 is equal to 32. So 32 is less than 50, which is less than 64. And I'm going to say because 2 to the 5 is less than 2 to the x. So again, I'm going to say that this is equal to x. And that's between 2 to the 6, okay? So therefore, the logarithm must be between 5 and 6. Hopefully that makes sense. I've just kind of written in words what I kind of just went over there. Okay, and so then for part B, it says use the calculator to find the exact value. So that's just putting it in my calculator. So log 2 to the 50 in my calculator again. Press the log button, put 2 in the little box underneath the log, then 50 in the big box, and then I should get 5.64385. And so to 4 significant figures, yes, that would be 5.64 and then 4, okay, to 4 sig figs. And there we are. Okay, and then final question here. It says for part A, to find the values of firstly log 2 to the 1, so that's just put in the calculator. If I put that in the calculator, I get 0. And then log 3 to the 1. And this is also equal to 0. Surprising. And then for the third part, again, we're then going to work out log of 17 to the 1. So if I put that in the calculator, I get 0. Interesting. Okay. And then part B, you're probably going to guess, explain why we get 0. So explain why log to the base of any base A, right, in general A, to the 1, any base A to the 1, has the same value. So it's going to be what equal to 0, right? But why is it equal to 0? Okay. Well, actually, let's ignore 0 for now. Again, as an exponential, if I call that x then, right? We're going to know x is 0, right? But we'll get to there. But what this is saying as an exponential, this whole thing, right? What that's whole as an exponential, that's saying a, my base a, again, I don't know what a is, it's just a general number. A to the power of x, my power x, equals 1. Okay, well, think about it then. No matter what number I get 1. Well, if you think back to your log laws, your power laws, sorry, what power do I raise by? What power do I raise by to always get me 1? 0, right? You should remember a to the power of 0 is 1. Okay? Anything to the power of 0 is 1. Except for 0, right? But, okay, we'll ignore that. We don't come across that. But anyway, anything to the power of 0 generally is 1. And so we can say that x is 0. But there we are. So it's equal to 0. Okay? And the reason for that is because of this exponential law, due to the power law. Oh, a to the 0 equals 1 for any a, for any value of a. But they said value of a, that of any positive values of a. Okay, so I should be more specific for any positive values of a, and a isn't equal to 1, right? Okay, so yeah, so anything to the power of 0 that we need, and it will always get me 1, and so that is the reason why. Okay, so that is that is logarithms. hopefully the main idea for now is you just get the gist of converting from a logarithm to an exponential, and the whole purpose of a logarithm is that it tells me what the power is, okay, what the hidden power is here, okay, and also how to use it, how to work it out in your calculator as well. But yeah, that's the main gist for now. That just setting up the backstory, the fundamental, the main principle of a logarithm, okay, and how it relates to an exponential. But yes, but next time we'll be delving deeper into logarithms for the remainder of the chapter. But yes, that's it for now. I'll see you next time.